Hi, my name is Marin Todorov, and welcome to this talk on Swift Modern Concurrency. I've been working with a number of asynchronous frameworks for Apple platforms. And lastly, I've put together a book on the latest and greatest, Apple's new Swift concurrency framework. I'm going to plug my book at the end of this talk. Now, the 30,000-foot view of concurrency in modern Apple platforms start with mundane error-prone code where you used to create and merge threads manually. Now, a little later, Apple released a higher level framework called Grand Central Dispatch, exposing C APIs using the construct of dispatch queues, which allowed to in-queue pieces of work to execute serially or concurrently on the queues. Now, at the time of its release, the 1.0 of Swift inherited the GCD APIs, so it had concurrency from the start. But with version 5.5, it's got new native modern APIs for structured concurrency that are integrated with a compiler in the runtime in a much better way than concurrency APIs were ever integrated before. Now, the elevator pitch about structured concurrency that resonated most with me goes something like this. If we take programs before structured programming, code looked a bit like a flat list of lines with only global state, where control flow was just go-to jumps back and forth in the listing to specific places without the notion of a call stack. Now, much of pre-Swift 5.5 asynchronous code is kind of like that. It executes these sparse closures and callbacks with no native way to properly scope the data, error handle, or return data to the caller side. And structured concurrency kind of fixes this and other existing issues. I'm sure you've already watched at least some of the WWDC 2021 videos on concurrency, and hopefully on Swift Doxy, and you're familiar with the basics of the new concurrent APIs. In this presentation, I'm going to shortly talk about 3 of the features of modern Swift concurrency: async await, task groups, and actors. And for each, I'm going to give you a 2-minute overview, expand on a few aspects that I find interesting, but maybe don't get mentioned very often, and also show a technical aspect that I find very, very interesting and kind of quirky. Okay, let's go. Let's start with the long-awaited async await language features. It comes around to 2 keywords, async and await, and how we use them together. In Swift 5.5, you can declare a function or a closure or a property getter as async, and that will execute its body in an asynchronous context, where you can non-blockingly await on calls to other functions, dynamically cancel asynchronous tasks, and use Swift's native error handling in asynchronous code. In the code sample here, we've declared load items from server, the function, as async. And we can call it from other functions or from closures that are async themselves by using the keyword await to non-blockingly wait for its completion and so that it returns its return value to us, to the caller side. So you'll mostly see similar examples out there on using async await like this one, which at first glance might seem to you like futures in other languages. However, unlike in other languages, as just mentioned, Swift has the notion of an asynchronous context, which allows the compiler to provide you with compile time diagnostics on your async await code and perform runtime optimizations for you. In this code sample, the SwiftUI view modifier on appear takes a synchronous closure that executes synchronously. So it doesn't accept you using the await keyword. That's why you have a compile time error there. Now, on the other hand, the task modifier accepts an async closure, and so you can await on async function calls. That code executes asynchronously at runtime on the so-called cooperative thread pool. So one day, as I was thinking about this, I saw this tweet from Tibor, who was mentioning the fact that you can define two functions with the same name, one sync and one async, and see which one the compiler picks in which kind of context. So I made a little struct with two methods called fetchID, like on the screen. One is synchronous and one is asynchronous. And this is the only difference between them. Arguably not a super useful example, but to try out what the compiler is doing in this test setup is just perfect. So then I call them from inside an onAppear vModifier in my code, and from the task modifier, which we already discussed in the previous slide. And so as expected, the first one, the onAppear, prefers the sync version of fetchID, and we can see this in the console because it prints sync work in the console. Then the task version, we also use the keyword await, of course, and that calls the async version of fetchID, and we can see in the console that there is async work printed out. Now, when I stop the debugger inside the task vModifier, I verify that the code is running asynchronously because it stopped in a thread called thread 4, obviously a background thread. Now, however, what about if we are not using the wait keyword in an asynchronous context? And so let's have a look at almost the same code with the difference that now I'm calling fetchID from onAppear and from task as well without using await. It looks like the compiler prefers the synchronous variant of fetchID, as you can see in the console, because both of them print sync work, therefore both of the calls actually invoke the synchronous version. So keep in mind that if you want the async version of a method, make sure you always use the await keyword. That gives you the right code path. The really interesting part is that the compiler actually sees that no asynchronous calls are made inside task. There's no await keywords at all in my task vModifier. And so it figures out that you don't really need an asynchronous context in there, and actually runs that code synchronously. So we can check that by breaking again in the task modifier just as before. And this time, the debugger stops in, as you can see there, com.apple.main thread, which is basically the main thread of the application where the rest of the my view code runs. And so this way, at compile time, the compiler makes this optimization for you so you don't have to switch threads unnecessarily. And that avoids switching between threads whenever it's, of course, necessary. If you need an asynchronous code, of course, the compiler will do the right thing. But if you don't, there's an optimization that runs under the hood for you automatically. And this kind of optimizations, they really add up if you have highly concurrent code. So I found that really, really cool. All right, now, next topic is task groups. Tasks are the primary unit for performing asynchronous work in the new modern Swift concurrency. And task groups are a way to relate tasks, process their results, or wait for them to complete, and also automatically error handle tasks as a group. And so you're going to mostly see this kind of examples so far. Creating a task group, running some kind of a loop there to add a bunch of tasks, which are in fact the same task, just with different input, to perform concurrently. And this is just fine. If you have a use case like that, where you have just a collection of inputs and you want to process them concurrently, that's a perfectly perfect good code. Task groups, however, can do much more than that. Here's an example of a user login sequence modeled as a task group. First, we start by adding 3 concurrent tasks running in parallel, waiting on the device location, asking the user to allow some system permissions, and connecting to the app's server API. And this will run concurrently, just as in the previous example. However, then we wait until, regardless of which tasks exactly complete at this point, if we get the result of the task that connects to the server API, we move forward, grab that connected client variable and move forward with work. And so we'll add 2 more concurrent tasks to the group. And so they will run concurrently alongside with the other ones that we initially added. Right, so the new 2 concurrent tasks are log in the client using the connected client and trace the login attempt. Here then we can now wait for all of the tasks to complete, the initial ones and also the ones that we added last. And so once they're all completed, we move on to asynchronously tracing the completed login sequence. And so this whole thing, this whole workflow of mixed concurrent and dependent tasks can be expressed with just a single concurrent task group. Right. So what is brilliant about these task groups is that they can completely and automatically handle errors. I find this very fascinating. Here's Xcode Instruments running a custom instrument that plots tasks that are running in a task group on a timeline. And so you can see that there are 5 tasks scheduled in the group, and the first 2, so we see here the final result after the task group ran, so we can kind of like introspect what happened. And so the first 2 tasks here on top that ran in the task group completed successfully, one after the other. Then the third one threw an error. And so once a task in the task group throws, all the tasks that have not completed are automatically canceled. As you can see here, the final 2 tasks in the task group that were just scheduled but not yet started on are canceled. And once this is finished, of course, the whole group also throws an error, so you can do your error handling outside of that scope. And this all happens asynchronously, and you literally have to take care of none of that. And now, another thing that I find really interesting is the automatic concurrency allocation for task groups. The concurrency framework decides how much concurrency to allocate for you. Here I'm running a task group, and I've stopped the debugger while the task group is busy working with many concurrent tasks. And I'm debugging the app on my iPhone SE. I see that the cooperative pool, which is a concurrent dispatch queue, is running 6 threads for me based on the number of CPU cores available on my device. And you can see the dispatch queue is also called com.apple.root.userinitiatedqos.cooperative, which is the cooperative pool on iOS. However, if I break in exactly the same spot on my Mac, I see that the cooperative pool is running many more threads. Of course, my Mac has more cores available than the iPhone SE. If you're running in the simulator, you'll get yet another amount of threads based on what the simulator gives you. And in fact, if you're testing on an older device, you'll get as little as 1 thread in the cooperative pool. The pool makes sure you don't spawn more threads than the available CPU cores, so you don't end up switching threads and slowing down your app instead of making it faster by adding concurrency. For the third and final topic, let's touch upon actors. Actors are a new first-class type in Swift, like structs, classes, or enums. Actors protect their state by running their code in what is called an isolation context. In this example, that you might see variations of out and about, the counter property is the state of the type, and the actor makes sure that any calls to increment the method are executed serially and sometimes asynchronously to guarantee exclusive access to the value of counter. And this way it prevents data races and/or crashes. However, using actors simply as replacement of locks is first inefficient, because they can do so much more naturally, and second, is just limiting yourself. Actors can do other, much more interesting things. For example, in this code, we group the few methods on the structures myModel and logger, and mind you, these are structures, they are not actors specifically, so they behave exactly like structures. But we group those methods from those structures together, and we also add to that group all properties and all methods on UI helpers. There's another structure, but instead of pulling methods separately out of it, we are just adding the whole thing on the main actor. And so this group of properties and methods and what have you, subscripts and so forth, will all run on the isolation context of the global actor, main actor. So let's rewind a little bit. We're not defining an actor that protects its own state. We're using the isolation context of an actor to add functionality from different types onto it. So this is really helpful. This and so smart, and so I find it fascinating. I think it's a great idea. Now this allows us to create these safe silos that provide safe access to shared state across types and possibly across modules and so forth. You can use actors to create these safe concurrency silos between different types, and you can have, for example, a bunch of different model types that all share an actor silo to safely update your database. Now, if you pull all the methods that update the data on disk into a separate global actor, that ensures that each of them can concurrently and asynchronously update that database file, automatically, completely automatically. Another group type, another group that you can create with a global actor is, of course, the state of your UI. So basically any type that updates the state of your UI needs to be grouped in a global actor. You already have a global actor by default like that created for you, the main actor, and that ensures that all this state is coherent and complete over time. Regardless, what I find really interesting is the actor's implementation. Actors automatically implement the actor protocol, which I pulled here on a slide. This is the documentation from developer.apple.com/documentation, which has a single requirement called unowned executor. So each actor type automatically implements actor, and the unowned executor is automatically created for you as well. And so it does in fact have no requirements currently, but maybe you could be able to do more flexible stuff with actors in future. The executor is a semi-exposed type that you currently cannot create on your own. That runs the code of the actor. So the executor, it's a little mind-bending. The executor is a serial kind of a queue that enqueues all code that runs on your actor. And so if you're accessing a property on your actor, the getter runs serially on that executor. If you're calling a method on your actor, that also runs serially on the executor. And so when all calls to the actor are automatically lined up like this serially on the executor, that guarantees that each of these has exclusive serial access to the state. I think it's pretty fascinating. And so if we have a look at the documentation of serial actor, the protocol, serial executor, the protocol, we will see that it basically does one thing, and this one thing is to serially enqueue jobs. So currently you can only use actors with predefined executor that serially runs code to protect the state, but documentation hints that in future you could eventually create your own executors to implement different actor behaviors. Off the top of my mind, what could be possible with custom executors? For example, how about an executor that holds off executing jobs until the machine is plugged in a power outlet? That sounds pretty useful. Or what about an executor that holds off executing jobs until the machine is connected to the internet? Controlling execution opens up so many different possibilities. I'm really excited for that to be available to developers, so we can create a super powerful, super flexible functionality with that. In fact, I think actors are going to become a really big thing in Swift. There is currently a new language feature in development adding distributed actors to the compiler. Distributed actors are actors that run in slightly stronger isolation context. And that allows them to run their code not only on a specific thread like the main actor, but also in a different process on your device, or even a completely different machine altogether, like a remote server in a data center. If you haven't seen the pitch, head on to the Swift forums. It's a pretty interesting stuff. The syntax is still in flux, but here's how it could look like to use a distributed actor. This is pseudocode. You would create an instance by providing some kind of identification and some kind of connection protocol. In my example here, I have a distributed actor called database, and it has a method called all users that returns some kind of user list from the database. And I'm creating an instance of it by calling database.resolve. And that creates an instance of the distributed actor by using the identification in the transport protocol. So I imagine that I'm connecting to a machine with a given IP, and I'm transferring data. This is this transport protocol that what enables me to transfer data back and forth to the endpoint that we're aiming at is an HTTPS connection. And in this code, the variable database that I use to call the all users method at the last line, this is kind of an avatar that you interact with in your own code, but that controls a remote instance that actually performs the work somewhere else. Different process on your machine, different machine in your office, or as we said, could be a server somewhere in a data center. And after the work is performed, it returns, possibly returns data back to you. And since all of these methods on distributed actors are async, it doesn't make any difference for you how you call the code between local actors and distributed actors. It's just waiting on its async functions. And it's really, really cool. To give you a glimpse into why I'm so excited about distributed actors, let's have a look at this setup, at this example. You're working on a code editor app with a plugin architecture. A plugin is a distributed actor that can modify the code or provide diagnostics back to you. And so a single distributed actor called here plugin, as you can see the three plugins kind of like encompassed in the code editor app there, will let you talk to the actual plugins that are running in separate processes on the user computer. So for example, plugin number 1 is doing syntax highlighting for you, giving you back the data in the main app. The second plugin can be doing on-demand code formatting for you, gives you back the results into the main app, and so forth and so forth. So these can be potentially dynamically added or removed. And the thing is, if one crashes, that kills its own process. And not only that, but if it actually crashes while you're making an asynchronous call to it, that will give you back a normal vanilla Swift error in your own code in the main app. So not only you won't crash, but you could also error handle that flawlessly. Flawlessly, I mean, yeah. And so let's expand that setup a little further. What if one of the plugins did some machine learning on the code and actually ran on some GPUs in a data center and not on the user's machine? You can use the plugin distributed actor without any modifications because, as these are async calls, it makes no difference for you if it's a local actor, if it runs in a different process, or actually in the data center. It's just making an asynchronous call, awaiting the result back. The only change you need to do is use a different kind of transport, as we said, actors need a way to know how to send data somewhere to the final to the endpoint and how to get it back. And so instead of talking between processes, you need to talk over, say, HTTPC to a server somewhere in your internet. And all of this is happening because of how the new Swift concurrency is modeled, how async await works, and how tasks and actors and all of these work in Ensemble. And that's a wrap. With that, I quickly showcased a few points that I had in mind for this talk, and I hope that the technical details ignited your interest about the new Swift concurrency. If you're interested in the basics, have a look at the WWDC 2021 videos on concurrency. Those are really solid and really interesting as an introduction. If you're curious to learn in detail about concurrency and see more sample code covering async await, tasks, task groups, actors, and distributed actors, check out my book, Modern Concurrency and Swift, at swiftconcurrencybook.com. You can find me on the Twitters as iCanZilb. And with that, thank you very much for your time. Goodbye.